Okay, we're looking at 6.1, and we just did our experiment where we showed, via Matt and Ethan's beautiful ball tossing, that horizontal motion doesn't affect vertical. If you look there on page 153, and I'm sorry I don't have a picture that shows this, they've given you a picture of what if we were to take snapshots every, let's say, hundredth or a couple hundredth of a second, we would have something that looks like this, the motion of those two balls, right? You see the red ball is simply falling straight down, right? But you see the purple ball is making that arc motion, right? Because it's been given some horizontal motion. What do you notice about the heights of the balls? They're the same. They're equal. All the way down the motion, right? And so again, I understand it seems like contradictory. It seems like it is not really the way it should be. But the point here is that horizontal motion is not affected by vertical motion. And of course, you can say vice versa. Vertical motion is not affected by horizontal motion.
So what if if he's still just keeping it on a perfect x-axis line,
yep,
still falling, but if he gave more force, it would still fall?
Ooh, this is a great question, right? So what if Matt threw it like as hard as he could, but it was straight level? Would it still hit the ground at the same time? Again, think back. What forces are acting in the vertical axis? Gravity and air resistance. Okay, we're assuming because we've got two spheres exactly the same, that air resistance is behaving the same on these guys, right? Okay, so just gravity. Does gravity change based upon how fast you're moving? It doesn't. So would they still hit the ground at the same time? They would. What would be the difference, though? It'd be further away from where it started, right? It would have a much larger x distance, right? What we call that is range. That's x distance, or x displacement of a projectile. Okay, your textbook gives a projectile definition as an object shot through the air. Okay? And that is the same just by dropping, just by throwing. You're making these things projectiles. Of course, you see where we're going. We're going to be talking more about our rockets, right? And the actual equation stuff we need to predict how it's going to move. That's why we're going here. Sir?
What about objects that are shaped the same, like a rocket, where it's like cone shaped instead of a sphere? Because travel, if you shoot one, because of aerodynamics, probably fall later because
Sure. Different shaped objects will give you different X's and Y's based upon their shape. I would completely agree with that. But the only force that's really still acting on it is going to be gravity. Now, you can get some lift and some drag that will affect that motion, but regardless, it's still going to be an equal piece. Does that make sense? If you have two things of the same shape, the lift and drag will affect it the same, so therefore just really gravity is working on it. Does that make sense? Yeah. Okay. Of a projectile. Sorry, just my bad handwriting. Are you with me, my friends? So what we have to think about when we're talking that these two axes are separate, okay? We're going to use the same type of equations that we've used in the past, right? Our equations don't change. We just simply use them in a slightly different way, all right? So let's talk about these guys. You remember this? The distance final equals distance initial plus velocity initial times time plus 1/2 at squared. Remember, this is just our classic acceleration. If I know velocity and I know time and I know acceleration, right? And then this would be just simply distance is rate times time, or distance is velocity times time, right? So for our x motion, this is the only equation we need. Excuse me. Does that make sense? Because if I've given a projectile, right, I can break its motion into its two pieces, right? Oops. Right? If I have something being shot this way, I can break it into its x and its y, right? Remember, this is what we did at the end of last semester, right? And I can look at these two things individually, right? Because what did we say? Horizontal motion does not affect vertical motion, right? So no matter what's happening here, it doesn't affect the y. No matter what's happening in the y, it doesn't affect the x. Does that make sense? All right, so let's go back to our equations. Are you comfortable that they're using this y, meaning vertical motion? Right? I can use the same equation, but it has an x. That would just be horizontal motion. But we're not dealing with any accelerations in the x-axis. We're dealing just with accelerations in the y. And again, what's our acceleration here? Not very gravity, right? Gravity, exactly. Okay. Yes, sir. Mm-hmm. It's a great question. I'm not going to answer it because I'm going to show you a little clip from Mythbusters where they did that exact same thing. Where they shot a gun, because again, this is the logical extension of the question that was asked before, right? If you throw something really hard, will it hit the ground at the same time? They said, okay, let's shoot a bullet and drop a bullet at exactly the same moment and see what happens. So we'll come back to that, because I do want to show you that little clip. Okay? But logically, I bet you can tell where it was going to go. All right, so let's look at on page 155, they show you this little problem-solving strategies box that's there. I do encourage you to check that out because it's going to walk you through how we're going to do these problems, okay? And they show you the equations that are present there. You've got your horizontal equation, which is just x is velocity times time, right? By the way, they put an xi here, right? Your initial velocity, just in case you gave it some sort of head start. But it's the same equation, right? And then they gave you the different pieces for the vertical acceleration, right? We have the middle one already up on the board here. Notice, by the way, they kept it as x, even though I changed it to y. Your textbook goes back and forth between those two things. The top equation, you see that, is just VF is VI plus AT. Right? These should look very familiar. They're the exact same equations we used the last couple of chapters, right? And then if you don't have time, then we have the VF squared equals VI squared plus 2A. Remember? YF minus YI, right? Just if I don't have time, that's the equation I'm going to have to use, right? So my point, I wanted to show you these, was that it's the same stuff, right? There's no difference with what we're doing here. Same equations. If you went back and looked at that spreadsheet that Mr. Kutzmer made for predicting how fast and how far things went, the equations he used were these guys. Okay? All right, so let's take a look at the problem, the example problem number 1 that's present here. Again, this is on page 155, 6.1. You're preparing breakfast and slide a plate on the countertop. Unfortunately, you slide it too far and it flies off the end. If the countertop is 1.05 meters above the floor, as it leaves the countertop at 0.74 meters per second, how long does it take to fall? And how far from the end of the counter does it land? So there's two things we're trying to find, right? Time and range. Range is a distance. Yep, it's an x distance. How far away from where you shot it from. Okay? So what do we know in this problem? What does it give us? Okay, so it's initial velocity. And is that velocity in the x or velocity in the y? It's in the x. Good. And I want to make sure you see that, right? Because it's sliding along the countertop. Okay, what's its amount? Good. 0.75 meters per second. Okay, what else does it give us? Okay, the acceleration of gravity. Okay, and there is wisdom making that in a negative. You don't necessarily have to, but that's fine. You can do that because we're not adding some velocity in the y direction, so we can go negative or positive there. What else do we know? What else does it tell us? The height. Okay. Sure. And can you see that in the problem that they called that yf, the distance in the y final, would be negative 1.05 meters? And the only reason that's negative is because we're starting here on the countertop, right? And what way are we moving? Down. And we've called down negative, right? Because we said negative 9.80. Are you with me? So therefore, here's my 0, the countertop, and we're going down to the floor. That's 1.05 meters. We cool? It would be, yep. The initial velocity in the x direction. Mm-hmm. Oh, I apologize. Thank you. Yeah, isn't that interesting? Yeah. In the actual known numbers, they wrote 0.75. In the problem they did was 0.74. Anyway, that's quite interesting. Obviously, it mixed up on the book's part. Okay. A couple other pieces that they wanted to make sure you know. What's our xi? What's our initial distance? 0. What is our y initial? 0. What is our velocity in the y initial? Would be 0. Right? In other words, this guy is it's not starting off falling, right? It's just starting off sliding. You say, wait, Mr. Hess, it has velocity already, right? 0.74. But that's in the x. Right, because it's sliding across the table at that velocity. We cool? All right. So, we want to find, let's go for the time first, right? So I want to find time first. And the equation that I have, that I need to find time, I know acceleration, right? And I know my distances, right? Right, this is 0, right? What's my YF? Negative 1.05, right? So I know my distances. I know my initial velocity, which was 0. I know my acceleration, that's gravity. I'm trying to find time. So I'm going to use this equation to solve this problem. I need to get time by itself. Are y'all comfortable with that? Okay. Now they just did the math for you and showed you the answer on page 155 in example problem number 1. Right? But I'll walk you through. Are you comfortable that this is 0? My initial velocity, my initial displacement in the y was 0. What's my initial velocity in the y? 0. So when you times that 0 times time, it's going to be 0, right? We cool there? Okay? In the x. We have it in the x, but not in the y. And again, that's the key piece. We have to make sure we keep these guys separate. They're two separate dimensions, right? Okay, so can we solve and get this t by itself? Can I multiply this by 2 to get rid of this half? Are you okay with that? Can I divide this by a? We cool with that? So I end up with t squared equals 2yf over a. How do I get rid of the squared? I square root it. So therefore, are you okay if I write this? That t equals the square root of yf, excuse me, the square root of 2 times yf over a. Now your textbook has it as 2 times yf minus yi over ay. Just want to make sure you see we canceled out that yi because it was 0. Are you with me, my friends? And then I simply plug in my numbers. 2 times, what was my final distance in the y? Oh, 5, yep, sorry. Divided by what's my acceleration? Negative 9.80. And I get a time of 0.46 seconds. So it takes about half a second for that thing to slide off and hit the ground. Are we cool? If I want to know what's the range, how far it went in the x, are you comfortable? I'm just going to use this equation here. I want to know distance. Distance is x, right? I need the velocity in the x times the time. Okay. So what was my time? How long was it in the air? 0.46, right? What was its velocity in the x? Ah, that goes back to the velocity they gave us at the beginning, right? 0.74. And I multiply those two guys together, and we get 0.34 meters. And they do mention it. I'm not sure what I just did. They do say to the right, because we're assuming that we've said that this is positive and that this is positive. So since I have a positive number, it's moving to the right. Does that make sense? I wasn't, and I apologize, I wasn't planning on lecturing you a bunch here, but I wanted to make sure I walked through this problem with you. It's the same equations we've been using, nothing different. The key point is that the y and the x motions are separate. So I can't just take that x velocity and plug it in for the y, right? I can't do that. I can't just take the y displacement, the distance, and plug it in on the x. You have to keep the x's and y's separate. Yes, ma'am? Because this was 0, right? My initial distance, my initial velocity in the y was 0. It canceled out. If it wasn't, if there was some initial y velocity, then we'd have to deal with that t. You're right. But in this case, we didn't need to. Okay? What I'm looking for you to try are these 3 problems, my friends, on page 156. It's 6.1. Page 156, it's numbers 1 to 3. Give them a shot. Again, we'll talk about them tomorrow, but give them a shot. You've got about 5 minutes. Go ahead and jump on it.